So, friends, welcome to lecture series of geomorphology, and in this class we are going to discuss about the soil formation process, some factors and how they influence the formation of soil at different geological conditions. Different geological conditions, once I say about this parent material, the climate, the organisms, the time, the topography, how those factors influence the degree of soil development and how those factors they change the characteristics of soil at different places. So, if you remember, we were talking something about this residual soil. Residual soils, they are of different characteristics as compared to their parent material. For example, if we see here, we have some certain rocks, and if you see this residual soil, the residual soil mostly it is a leached soil, it is a extremely leached soil. So, that means those unstable minerals which are here, or the unstable means which are chemically unstable, they are removed from this part and they are getting transported and deposited or accumulate somewhere here. Similarly, if it is in alluvium or it is the porous medium and permeable medium, they also leach down and will accumulate somewhere in this zone. So, that is why this residual soil which is of totally different characteristics as compared to this parent material. So, residual soil mode of formation does not involve sedimentation or consolidation process. So, here only leaching is there. Okay. Residual soil properties shows considerable variation in terms of their engineering property from top to bottom. In these two photographs, if you see here, this is in situ granitic regolith. That means, this parent material is granite and this is the thickness of this residual soil developed. Granitic mostly quartzo-feldspathic rocks. Now, if you analyze this chemically, this part, it will be more rich in aluminum. So, there are examples also a sandstone body which is by chemical leaching, by formation of the residual soil, it becomes a economically viable aluminum deposits. I will discuss in the later stage. So, now you see the transition is observed gradual, relatively fine material found near the ground surface and they becomes coarser with depth to reach the larger fragment of stone. So, here once we are going downward, here finer materials will be there and relatively coarser material, and this regolith again these are the coarser material will be here, and finally, the bedrock. But within this system, suppose for example, here one property like this electrical resistivity is given there, and this is the resistivity value, and this resistivity value, the change of resistivity value, that depends upon the change of the characteristics of soil. Somewhere there fractures are there, water will be percolate there, this part will be more moisture conditions. So, their resistivity value will be there. So, there are different soil properties once we measure, it will be completely different from their parent material. So, residual soil is totally different characteristics it shows from their parent material. Here is the example we are talking about, it is the bauxite deposit of Weipa, Queensland, Australia. So, this is a classical example of residual soil. How? Now, you see in this figure, this is the parent material, this part it is the parent rock, parent material. It is composed of near about 90% of quartz and 10% it is kaolinite or clay. Now, this is the depth, it is from 0 to 10 meter depth or more than 10 meter depth. Now, you see this bedrock is a sandstone consisting of 90% quartz and 10% kaolinite. Under hot monsoonal climate, with strongly seasonal rainfall averaging more than 1500 millimeter per year. Most of the quartz has been leached to a depth of greater than 8 meter, and the upper 5 meter is mostly hydrated aluminum oxide, that is called gibbsite. So, now that means I want to say, if you confine yourself up to this depth, that means you are getting an economically viable bauxite deposit. However, if you compare this bauxite deposit with its parent material, this bauxite deposit is evolved from a sandstone body simply. So, that means the residual soil or the residue of weathering, it is also of totally different quality, different characteristics as compared to this parent material. So, this indicates that surface bauxite ore is a residuum of quartz sandstone at depth. So, thus residual soil can be vary of different form and different characteristics as compared to their parent material, given the right combination of other 4 soil forming factors constant. So, that means structural or parent material control on weathering is an important soil genesis, and it is also important in landscape development. Now, after parent material, the climate is another important parameters in soil development, and if you compare this parent material and climate, none of these two wants to take the second position. So, climate and parent material both stand equal, because climate influence the soil composition, the soil characteristics as the parent material. For example, if you see here, climate must compete with parent material for the status of first among the equal in the list of soil forming process. Now, here you see, depending of the climate, few factors has been assigned. One is this blue line in this graph, it represents precipitation, and precipitation now you see it is varying from, it is somewhat more here, less here, and again it is highest here. Similarly, evaporation, here evaporation is less than precipitation. In this part of this graph, evaporation is less than precipitation. So, that means precipitation is more, that means the area remain moist, it remain waterlogged. Similarly, in this area also see evaporation and precipitation, the difference is this much, this area is waterlogged, this is moist. But in this case, in this part of this graph you see, this is rainfall is less than evaporation, that means here more evaporation, less rainfall, that means dry area. Similarly, the third parameter is temperature, the red line that is indicating temperature, and gradually in this graph the temperature increasing from left to right. So, there are 4 parameters here. One is this line, it is indicating the evaporation, this blue line this is indicating the rainfall, this red line the indicating temperature, and this green line it is the vegetation. So, these 4 parameters, how they influence the soil characteristics, how they influence the degree of soil development, the soil thickness, it is been discussed here. For example, consider this part of this graph. Here most and temperature both diminishes to north, hence weathering is slow, organic matter decomposition is low, and either the slight precipitation, the permafrost or the tundras inhibit leaching of mobile constituents. Consider the second part of this graph, high moisture promotes high leaching, because water is the most culprit of weathering. So, here high moisture content, because here precipitation is more than evaporation, that means high moisture content will be there. So, high moisture content promotes high leaching, relatively low temperature results relatively low rates of organic matter decomposition, that is why thin soil development. Then consider the third part of this graph, this is first part, this is second part, this is the third part of the graph. In the third part of the graph, if you see high temperature aid chemical weathering, but low moisture inhibits vegetation, organic matter buildup and leaching of the mobile constituents. So, that means here it is high temperature condition, it is succeeding, it is more influencing than other parameters. Here more evaporation will be there because more temperature, and here rainfall is less, isn't it. So, that means temperature, once its temperature is high, it is chemical weathering is more, but to promote this chemical weathering we should have other parameters also supporting to that, but unfortunately here other parameters are not supporting. But if you consider this part of this graph, here high moisture content and temperature results in rapid weathering and high rate of leaching of mobile constituents. So, that is why here if you see thick soil development is there. So, this is the ideal conditions. If you compare this relative role of these parameters, by variation of these parameters slightly, that changes the soil forming process, they influence the soil formation process. So, that is why different soils of different thickness, different chemical properties, they varies depending upon the precipitation, evaporation, temperature, vegetation cover like this. So, that is why climate and parent material, none of them wants to take the second position for influencing or defining the soil profile and defining the soil characteristics. Climate, in briefly, the most powerful soil forming factor. It is both temperature effect and rainfall effect. Temperature controls rate of chemical reaction. Warm region soils are normally more developed as compared to this cooler region counterpart. Rainfall affects leaching, pH and soil aeration. So, according to soil scientists, it is very important to note, according to soil scientists, similar soils can be produced from different parent material in same climate. So, climate influence is so intense that from different parent material, similar soil can be produced in the same climate. Similarly, dissimilar soils can be produced from same parent material in different climate. So, that means I want to say climate and parent material both plays important role in defining the soil characteristics. Here again the old graph, there are different weathering segments defined by our rainfall and this temperature variation. Climate is the single most important factor in soil formation. Climate influence the rate of weathering, in which turn control the soil thickness. Rate of weathering and soil thickness, the more rate of weathering, the thicker the soil, and the reverse is also true. The rate of humification, that is breakdown of organic matter. Then the amount of leaching is the process where minerals are washed downward, leaving the layers soil without minerals. So, that means soil composition will be changed. Soil that has been developed in response to particular climatic condition are called zonal soil, arid zone soil, humid zone soils. So, if it is characteristic of a particular climatic condition, that is called zonal soil. Chemical weathering is more prevalent in warm and wet tropical climate. Mechanical weathering is more prominent in cold and relatively dry region. So, that is why depending upon this climatic condition, different parent material or same parent material in different climatic condition, they will produce different type of soil. Similarly, different parent material in different climate, they can produce same type of soil. That is why climate plays important role as parent material in defining the soil formations in soil characteristics. Then the third parameter is topography. Topography, it is a changing parameter. So, it changes with time like climate. at one place, it is at geographical location in a geological time scale, climate may change from different climate can be changed. So, that means one geographic location, the undergoing humid climate nowadays may be in geological past it was in arid climate. Similarly, topography also change with time. A topographic inversion we have already discussed in our weathering classes. So, topography influence the soil forming process is emphasized more by pedologists than by geologists. For example, suppose we are talking about these photographs or this figure. Here if you see this black color regions, that is the thickness of the soil. This is less thick soil or the thin soil is developed, but once you coming to this topographically lows, the soil thickness gradually increases and again decreases at the topographically highs and it becomes 0. That is why in this region the R horizon is exposed, and this is a flat region, this is a sloping region. So, in the slope the soil formation is less, but in flat the soil formation is more. So, if the slope is steep, runoff is rapid, erosion removes the soil as fast as it forms and little water enters into the soil and the profile is thin and poorly developed. However, if you go to the low lying areas, flat lying areas, the soil thickness will be more as compared to this sloping areas. Here another photograph is showing also the same. Here you see this is a flat topography. In the flat topography we are getting thick soil development and it is a very steep slope, here there is no soil at all. So, that means higher slopes promotes less soil development and flat region they promotes more soil development. Then the fourth parameter, it is called organisms. A factor of soil formation have been reviewed in their role as chemical and biological weathering agents. Organisms utilize easily digestible minerals like simple sugars, carbohydrates and found in the parent material, leaving the more residual material such as fats, waxes behind. So, that means suppose we have organic influence in that here. So, organisms they utilize the easily digestible minerals, easily breaking minerals like the simple sugars, carbohydrate. So, in this region of the soil this material will be less. However, these more resistant minerals or the most resistant part of the organic matter that will be rich in this area and we have parent material, we have minerals. So, now the most resistant part they will intermix with the parent material and forming one globules or forming one material, a unit cell that is called PED. So, those materials which is left behind is not easily decomposed, it comprises the humus found in the soil and these humus particles they interact with the rock particles or the minerals and if you see here this is called soil particles or this is called PED. So, humus act as gluing agent essentially holding the primary soil particles sand, silt, clay together form aggregates that is called PED and PED is the unit soil particles. Whenever we talk about pedology, pedology means it is the unit soil characteristic unit soil particles, it is a mixture of humus and these soil particles like sand, silt, clay they mix together and forming a shape, this is called PED. And if you see the individual soil particles aggregate to form soil PED and PED are stacked around each other to form soil structures. So, that means here starts our pedology, the soil science. PEDs that is the structural units are called PEDs and have distinct boundaries and well defined planes of weakness between the aggregates. Bed consists of primary particles bound together by cementing material like organic material, clays and hydrous oxide of iron and aluminum. Beds are taken several shapes. So, whatever we are talking about the beds, their shape varies and there are different parameters that define what shape a pad will take. So, the pads may be of granular shape, small grains, granule type, sometimes of pad are like that. The pads may be blocky, blocks. So, within that blocky there is subangular blocky or angular blocky. That means, if angles are very well defined, then it will called be angular blocky, or like angles are not very sharp, it is subangular blocky. Similarly, platy means plate type of appearance, that means the pads they are plate like. So, plate like may be due to compression, it is comprised like that, or it may be due to this clay mineral, due to presence of clay minerals as binding agents. Clay minerals have inherent property to be flat, plate like. So, platy may be like this. So, lenticular means lens type. Lens type, if you see here the pads, it is of lens type. Similarly, wedges, it is wedge, then prismatic like prisms, columnar like, then single grained or massive. So, that means, depending upon the geological condition, depending upon the climatic condition, depending upon the degree of compaction. So, the soil structures vary their shape, like from granular to massive, blocky, subangular blocky, angular blocky, lenticular, platy, like that. Then the fifth soil forming process or soil forming parameter, it is called time. Time we cannot change, parent material we cannot change. So, all other three factors that change with time. So, arrangement of soils in time, it is called soil chronosequence. So, that means, I want to say, suppose in a particular area we confine our study. So, all soils in that area, they are not formed at the single geological time. So, that means, we have soils, some of the soils they are developed on the older parent material, some of the soils developed on the younger parent material. So, if we arrange those soil development or arrange those soils with time in a particular area. So, this stratigraphic arrangement of soil, the stratigraphic arrangement of development of soil with time, that is called soil chronosequence. So, soil chronosequence, it indicates the geomorphic evolution of an area. For example, if we take this study particularly in the Ganga plain, here in this figure it is shown, this is river Kosi and this is river Ghagra, and here will be river Ganga somewhere and here Yamuna somewhere. Okay. So, now our study indicates these are the different soil, these are the different geological features or geological area, geographical area which is defined by different soils. For example, if you see here, this is this symbol indicating the soil which were developed more than 10,000 years back. So, that means, this area or this geomorphic unit indicating soil which was developed greater than 10,000 years ago. Similarly, this geomorphic unit, it is indicating the soil which was formed 10,000 years ago, and this and this. So, that means, in an area when we are going for a geomorphological mapping, we characterized that these soil were formed in 10,000 years back, and later from 10,000 to 8.4 thousand years ago, these soils were formed. Suppose this soil, it was formed from 10,000 to 8.4 kilo annum. Similarly, this soil 8.4 to 6.9, this 6.9 to 4.7, and 4.7 to 1.4 and less than 1.4. So, that means I want to say if you stratigraphically arrange these soil forming processes or the stratigraphically arrange this soil geomorphic unit, this will be the younger one, it will be in the top, and this will be older one in the bottom. So, that means this will called soil chronostratigraphic sequence, soil chronosequence. So, that means a geological processes which are acting here, they are the younger geomorphological processes, and here these are representing older geomorphological processes. So, that means how geomorphic process varies from one place to another place, that can be detected by the soil chronosequence by mapping of this geomorphological events or the geomorphological features. Okay. So, soil chronosequence of area that also indicates the climatic condition in this past, the tectonic scenario in the geological past, the parent material it was there in the geological past. So, that means I want to say the geomorphic evolution of an area can be well established through soil chronosequence, and soil chronosequence is nothing, it is time based arrangement of the soil in a particular area. Do soils and landscapes reach some end in a closed system and cease to evolve, or do they reach some dynamic equilibrium between the process and form maintained thereafter in a steady state morphology, even though energy and matter continues to move through their open physical systems. So, now the question arises, if we have parent material, we have climate, we have topography, we have the geochemical processes going on or this organic processes going on. So, soil formation will take place. Now, the question arises whether this will continue forever or there will be some stoppage, there will be some full stop, to what extent soil can evolve. So, soil formation will continue until unless the area is cut off from the main atmospheric conditions. So, once it becomes cut off, so that means a new process is covering it up, new sediment is covering it up, then this soil formation ceases to operate, because it is cut off from the atmospheric condition, and that soil becomes paleosoil. So, from Precambrian to recent, if you analyze the geological that cross sections, there are many paleosols horizon reported. However, the paleosol characteristics varies with time, varied with parent material also. So, a paleosol which is developed in the granitic gneiss migmatites in central Indian shield may not be as same characteristics that will be developed in the Aravallis. Similarly, the paleosol which was formed in Proterozoic sandstone of Pranita Godavari basin may not be of same characteristics in the Vindhyan basin. So, that depends upon the climatic condition that time. So, that means I want to say the soil formation, it is a closed system, in a closed system and in an open system. So, the soil formation it will continue until unless it is cut off from these systems. A basic issue of pedology is whether soil continue to evolve as some function of time, which might be linear, logarithmic or exponential, or whether they reach equilibrium with land surface lowering, so that at steady state of soil profile and weathered zone move downward through the rock mass as the surface is lowered. So, this question has to be answered to what are the factors that influence the stoppage of soil forming process. Research studies show that soils of several millions year old continue to evolve. Such long term weathering must have been in the progress during very significant late Cenozoic climate change. It is very important to understand. Suppose for example, we have soil of Precambrian time, but that soil that was cut off from the main body So, that becomes Paleosol. So, Paleosol, do they evolve? They can evolve if they are exposed to a particular climatic conditions. They are exposed to the particular climatic influence. For example, we have late Cenozoic climatic change. There are many times this earth has been freezed and defreezed. So, Paleosol is there, but it is totally cut off from the main body, cut off from the atmospheric climatic change. So, that means it will not be influenced, but once they are exposed or this climatic change is influencing to certain depth within which the paleo soil is confined, then it will change. So, that means such long term weathering must have been in progress during very significant late Cenozoic climatic change. So, those climatic change events which are influencing to certain depth of this from the earth surface, if the Paleosol is lying within that, so that means it will influence this form, it should influence its characteristics, otherwise the soil will be in isolated form. So, in soil chronosequence, a succession of coastal or river terraces, glacial moraines, alluvial fens and other landforms of progressively greater age, but with similar parent material, vegetation, slopes and climates are shown to have soil profiles with progressively greater development. It is very important. So, here this is shown here in these photographs. Now, you see we have parent material same, climate same, vegetation same, chemical activities or the geochemical activities same, organic matter same, but time is different. Now, you see here if I arranging the soil formation process or the soil profiles with time, here we are in this way we are decreasing time, this is increased time, this is decreasing time. So, here time is 0 and it is time about 10,000 years, 10k years. So, now you see there is a gradual decreasing trend of soil thickness. So, that means it I want to say provided that there will be parent material same, climatic condition same, this organic matter evolution same, but if the time is changing, with more time we are developing more thick soil. So, that means the thickness of the soil, provided that all other parameters remain constant, the thickness of the soil, it is indicating the degree of stability of an area. So, more thicker the soil, more the area is technically stable, and more time is involved, more thicker soil will be formed. Here is a classical example of soil in the Ganga plain. So, now you see the soils are arranged in with their time or this the age. This red color part, they are indicating soils of more than 11.8 K, that means it is the Pleistocene Holocene boundary, it is the Pleistocene cell. And this soil green color, it is indicating this is the time frame, yellow color this is the time frame, and gray color this is the time frame. And if we analyze the thickness, this time or this time frame that creates a thick soil as compared to this and this. So, that means with lowering time, the soil horizon thickness is also decreased. This is seen here. That means more time, more thick soil, less time, less thick soil or thin soil. And there are certain breaks within the time frame. So, for example, this is the slope and this is the slope break here and here, these are the slope breaks recorded. These slope breaks that indicates the tectonic stability. That means this area, this part, the soils were formed, some geomorphic process was involved, this area some soils were found, some geomorphic process were involved, and these breaks, there is a sharp break in this graph that indicating, that means this area was tectonically stable period, because in Ganga plain it is a tectonically active region. Here the soils are formed in a particular area, and once it is cut off from this main atmospheric condition. So, that means it is buried from the younger sediment, the soil formation stops. So, three sets of processes are seen in the soil chronosequence. First, in arid region, especially the addition of material takes place. In arid region, addition of material, addition means what is adding? Addition of silt and clay to the soil by wind with significant addition of Ca2 plus and weathered silicate, carbonate, dust and Na plus from sea water. So, in arid region these materials are added with silt and clay. Then second process is the transformation for of minerals, especially the progressive alteration of clay minerals and silicate to table hydroxide. So, this is the transformation process. The third is the transfer to various soil components and progressively greater depth. So, three sets of processes are found in soil chronosequence. First is your addition, second is transformation and third is the transfer, and finally, a soil sequence is formed. Chronosequence and desert soil can be based on the extent of secondary minerals accumulation, especially the calcium carbonate and sodiums. So, here the desert soil, it is based on the chronosequence is based on how much material is added. The more material is added, the more old the soil is. Similarly, in alluviums, the calcrete development. The more the calcrete developed, the more thicker the calcrete horizons, the more older the soil is. Okay. Because if you see, calcretes have different stages, and first stage for less time, then more and more time increases, these different stages are developed. So, that means calcrete is a massive shallow accumulation of soil carbonate that may be meter for more thick and may effectively control the scarp formations. So, in arid region, this addition of calcium carbonate, it indicates the degree of soil development or the time of soil development. The more material is added, the more old the soil is. A series of 6 stages of calcrete development has been discussed here, starting from stage 1 to stage 5. If you see here, in stage 1 only some calcium carbonates granules are developed. With stage 2, the more and more granules are added to it, and third, these granules are added with each other, and fourth, there are coalitions of that, and fifth, there is complete development of horizons. So, these are the different stages of calcium carbonate horizon development in the soils. In arid semi-arid soils has been established ranging from few percent of CaCO3 to that form coating on the pebble, that is on stage 1. So, stage 1, it is represented the coating, calcium thin coating on the calcium carbonate on the pebbles through layers of coalescence of nodules, that is stage 3, to massive cemented surface layers 0.5 to 2 meter thickness, which 25 to 70% of the soil mass is pedogenic calcrete, that is stage 4th to 6th. So, these are the degree of development of calcium carbonate, these are the degree of development of calcrete. So, in arid region, these calcrete development stages or the calcrete development thickness, the developed calcrete thickness, that depends or that says, that indicates how old the soil will be. More the older the soil, the more degree of calcrete development is there. Stage 1, soil ranges from Holocene to Pleistocene. Stage 4 and older calcrete horizons are found land surface that ranges age from 1 lakh year to several millions of years. So, these are the development of calcium carbonates. Okay. So, this is the characteristics of the soil, which is characteristic of arid region. Most of the carbonate that has been accumulated in dry soil is probably derived from wind blown dust size fragment of calcium bearing minerals that were previously weathered by hydrolysis to carbonation in different carbonate solutions and precipitated as calcium carbonate and blown by wind. So, whatever the calcium carbonate in the soils, many of these cases the carbonate calcium carbonate is not in situ. Once upon a time they were weathered somewhere else, they were as a dust, they were transported by wind action or transported by water action, and now they are precipitated with suitable climate, they are participating or precipitating within these soil pores. So, that is why a calcrete horizon is developed. Now, if you go to this Ganga plain, in Gandak region, the paleochannels, if you analyze from the satellite imagery, that will look like white appearance. So, this is nothing rather than the calcium carbonate precipitation. So, in this catchment area, we have calcium carbonate rich rocks, and this calcium carbonate it is dissolved within the water. Now, it is once it comes to this Gandak region, due to evaporation of water, this calcium carbonate is precipitating and forming calcrete horizons there. So, more thicker the calcrete horizon, more older the soil is. Similarly, here if you see, these are the calcretes, developed in a terminal fan, this is Aligarh terminal fan, it is from here, this is from Aligarh. Some but lesser amount of calcium carbonate are derived from weathering of place from upward or lateral movement of groundwater. So, though we have calcrete horizons developed, but maximum calcrete horizons they are not in situ origin, they are transported once upon a time, but less amount is precipitated from the rock itself, from the alluvium itself. So, here I stop, and in the next class we will talk about the soil classification. Thank you very much.